For this meeting on multi-method astrophysics, I'm here to review what one can learn about neutron stars in coalescing binaries with gravitational waves alone. The short answer you already know. The gravitational wave signal from long duration neutron star binaries encodes mass, so often only the chirp mass, sometimes spin, sometimes tides, depending on the signal amplitude. Indeed, with ambiguous objects like 1908-14, that first comment, seemingly prosaic measurements of the neutron star mass, are having increasingly high significance. To give a more quantitative and practical answer, I'm going to draw principally from the two studies below. You can use them if you like to find a more comprehensive literature review of this relatively well-traveled subject. So this talk has two parts, binary neutron stars and asymmetric binaries that may contain a neutron star. Each type of binary offers its own special advantages. For binary neutron stars, we know by example that we can measure tidal distortion. This allows us to directly constrain the nuclear equation of state, which I'll do increasingly well with more data. However, due to strong degeneracies, each individual measurement will produce weak constraints on critical factors like the individual neutron star masses. For asymmetric binaries, by contrast, gravitational waves have broken degeneracies, enabling much tighter constraints on the smaller component's mass at the expense of losing sensitivity to its spin and tidal deformation. So we're faced with a dilemma. For multi-messenger astrophysics and equation of state constraints, knowledge of the neutron star mass, and particularly the maximum allowed neutron star mass, is critical. But how do we know something is a neutron star? Well, one approach is to use the population to make statistical statements. For example, pulsar surveys have measured many neutron star masses to various degrees of precision. From there, one can reconstruct the underlying mass distribution of neutron stars, modulo some assumptions. On the left, you can see the inferred neutron star mass distribution for three subpopulations that the authors have identified, neutron stars and binary neutron stars specifically, and more general subpopulations of neutron stars, including those which have created some angular momentum and mass from a companion. On the right, making some stronger assumptions, you can see an inferred mass distribution for all neutron stars, assuming they're drawn from a single universal distribution consisting of two Gaussians plus a sharp maximum mass cutoff, and ignoring any dependence on evolutionary channel. The maximum mass cutoff is presumed to be imposed by the nuclear equation of state. As these two examples illustrate, even with copious data, the answer one obtains depends on one's assumptions, sometimes one's population and astrophysical assumptions. This is complicated because, in the gravitational wave case, not the pulsar case, because gravitational waves for emerging binary neutron stars are highly degenerate, with a mass ratio, spin, and tides all providing competing subdominant effects. As a result, gravitational waves of binary neutron stars don't strongly constrain the individual neutron star masses, and our inferences depend strongly on our prior knowledge of the binary neutron star population. As an example, I'm showing here the posterior distribution for both component masses for 1904-25. The inferred mass ratio, as you can see here with the two color scales, depends strongly on whether to allow one or more of them to be strongly spinning. If we had prior knowledge of likely neutron star masses and spins and mass ratios, our inferences about any individual event will be different, possibly dramatically different and sharper. Indeed, as we'll see below, you should always reassess our observations in light of the full population, even if the bulk of that population is poorly constrained. So what happens if we combine all information, mass, spin, and tides? Well, we're going to put in. But to illustrate this more concretely, I'm going to use a synthetic survey to identify, to illustrate this process. We're going to inject specifically a two-component mass distribution shown to right, motivated by the Elsing et al. Paper, which is going to use an APR4-like equation of state, which has a quite high maximum mass. You can even see it on the scale to right. The dashed red is the injected distribution. On the left, you can see our recovered population's chirp mass distribution as a PDF and CDF. Because of the survey selection bias in this recovered population has a more pronounced time mass peak. For scale, we've shown two vertical lines to illustrate some useful mass scales corresponding to binaries with those masses. So what we did is we studied how well we could recover our inputs with increasingly more observations, repeating our experiments many times. For example, in the gray solid line, the gray dashed regions show the posteriori distributions and credible intervals for the recovered distribution for the neutron star mass. And you see that in this particular case, we recover the injected distribution. In fact, we can recover not only the both components' mass distributions, but also their spin distributions, in fact, with only a handful of observations. In the right figure, what we're doing is we're showing the mean and width of each component of the distribution. You can see there's a narrow, very low spin solid black line, and up on the right, a more diffuse high mass component with a significant spin. With only one event, we will identify one or the other population, depending on which it's drawn from. With 5 events, we can in fact identify both with reasonable accuracy, and with 10, we do even better. And the multiple copies for each color indicate different realizations of our sample. So what does this mean for the nuclear equation of state? Well, gravitational wave measurements can constrain tidal deformability, which is typically denoted lambda for each object. And these tidal deformabilities depend on the neutron star mass and equation of state. So, putting it as an inverse problem, we can infer the nuclear equation of state with gravitational wave measurements, most famously demonstrated with 1908-17. On the left expressed as a pressure density relation, and on the right expressed as a mass radius relation. There's a few individual constraints, individual nuclear equations of state shown. Gravitational wave measurements of tides provide only one perspective on the equation of state. Other X-ray observations famously also constrain the neutron star size, most famously recently from NICER. But very strong constraints also come from known pulsars. The equation of state must be able to produce neutron stars with the observed masses. And as you can see in this figure from the NICER paper below, showing the sequence of adding in information, that information from the pulsar constraint is extremely strong. And 08-17 provides a lot of the remaining constraint. So what happens if we perform our synthetic survey? We combine all this information. We recover what we put in. No surprise. But did it matter that we used all this extra information? How much did we gain by using that extra population information? So to assess this in our synthetic survey, we made a very simple change. We repeated our analysis using a population model that was not sufficiently complex, that didn't have both subpopulations. This introduces a bias in our recovered mass and spin distribution, which in turn is going to propagate directly into biases in our inferred equation of state. So let's see how important that joint inference really is. Are we really dominated by the loudest 2 events, or is there something more to say? So to express our result, what we doing here is, this is a lot like this figure that I was showing before, the pressure density. We've selected a few different nuclear densities, and we're showing the range of pressures at nuclear density, twice nuclear density, and 6 times nuclear density, precisely those vertical bars shown here. The width of the violin plot on the extent is showing our conclusions about the nuclear equation of state at that density. Now, we're performing several different survey sizes, 1, 5, and 10 here. And you can see that we are recovering what we put in. And with the width of the error bars getting smaller as we increase the number of events. If we use, however, an oversimplified equation population model, then we will get biases in the recovered equation of state. In other words, that population stacking information, far from being an oversight, and far from being allowed to just choose some arbitrary fiducial prior model, self-consistently fitting that is important, and not doing it correctly, even just not correctly enough that we don't have sufficient flexibility to include the truth, will bias us. So we've seen that joint inference is critical. It's critical to use maximal information together to get the correct answer, because you'll misinterpret it if you don't. And conversely, it helps you use that correlated information from gravitational wave constraints more efficiently. It's also practical, and we'll get back to that to the moment. Now, however, we have clearly asymmetric binaries as well. To use that as a recent example, 0814, the figures below show asymmetric binaries can produce much sharper constraints on individual components. The figure on the left shows the inferred masses of both components. In particular, note how tightly the neutron star mass is constrained to a fraction of a solar mass. Similarly, the black hole mass and black hole spin are surprisingly well constrained. The neutron star mass, black hole mass, and black hole spin are, of course, all critical ingredients in for any calculations people are doing with multi-messenger astronomy to calculate brightness, ejecta, tail disruption prospects. So why can asymmetric binaries be so well constrained? So in what follows, what I'm going to do is use a specific synthetic source, actually a pair of two synthetic sources that are going to be shown in thin red and thin blue. As there we have absolute certainty, and we know what we've been injected, we can control for every single effect. In short, asymmetric binaries have a larger phase space that can include precession, and to a less extent, they also are more strongly emitting higher order modes, and both of these break some degeneracies, enabling sharper constraints. So what this rather messy figure is showing is precisely the posterior distributions derived for these two configurations, shown in Chern mass and mass ratio, and you can see quite sharp constraints on the component masses for the two configurations, solid and dotted with and without using higher order modes. The important thing to take away of this figure is, in short, over several years using carefully controlled experiments, we've learned what we can measure and why, particularly for black hole neutron stars. The principal reason that asymmetric binaries break degeneracies is a phase space where precession is very important. In these binaries, which are dominated by the single spin, the black hole spin, orbital angular momentum usually precesses simply around the total angular momentum, producing characteristic modulations in the signal. The trajectories and posterior distributions for precession are shown here. You can see it's simple precession trajectory. It's largely a circle over time as the orbital angular momentum decreases in magnitude because it's spiraling inward to a tighter orbit. What will happen is the angle between L and J will slowly increase, producing this spiral effect, which can occur for many cycles, depending on the magnitude and orientation of L. Depending on the source's geometry, you can get a different nature of modulation of the signal, because whether or not L points towards you or away from you produces stronger or weaker gravitational waves. You can see on the bottom that these modulations can produce extremely strong constraints, not only on the intrinsic parameters, but these orientation parameters, the angle theta Jn between the line of sight and the total angular momentum, and also this precession opening angle. Both of these can be measured with high precision, if in fact these modulations occur. Both of these are not only strong and significant effects, but they're also analytically tractable. So what one can do is go through and produce simple analytic calculations to demonstrate that we have control over what these posterior distributions should look like. Specifically, one can use what's known as a Fisher matrix calculation. So one way to do a Fisher matrix numerically is you can just generate the gravitational waveform, basically take some derivatives of it, compute some inner products, and you've got a Fisher matrix. You can also do this analytically if you happen to know the analytic form for your waveform. And for a simply precessing waveform, there's a pretty reasonably good approximation that you can do in the frequency domain. And therefore you can construct this Fisher matrix. This agrees reasonably well with the numerical Fisher matrix and with full posterior distributions, which means, in short, that this simple approximation, and there it is, that's all of it, that resembles precisely the calculations that one would do for a non-precessing binary, can tell you how accurately you can measure the mass and spin of a precessing black hole with arbitrary orientation relative to your line of sight, with arbitrary precession content. So this is quite helpful for people who need to do projections for future instruments, who need to assess whether or not there are prospects for measuring tidal disruption and coincident candidates. So if you've done similar calculations before, this should be pretty straightforward. You just compute these matrices, add them together, diagonalize, and you're done. Now, if you would rather just do full PE, I really want a fast, no approximation calculation, Dick and I have a code that does that. We can do that too. But many of you might want to use this approximation as it is a little bit simpler. So going forward, LIGO is providing an abundance of observations, filling gaps in our knowledge left and right. Conversely, it's creating new synergies with ambiguous objects whose classification may well depend on prior observations, and reconstructed populations to tell which objects likely contain matter. As a result, it's really essential to use all available information from existing observations. Fortunately, both theory and even code to do this are all widely available. I've emphasized my groups in this talk, and there are some links to some of the tools that will allow you to do all of the work that is described here, including the binary neutron star work, which should be made public shortly. So hopefully this means that these sorts of calculations will be something that you and your group shouldn't be able to have to shy away from, but should be able to embrace and integrate when pursuing your own objectives. So unfortunately, I myself am not able to be present today, but I believe my students may be during the session's question and answer session. So hopefully this will provide good food for thought. So please, thank you for your time, and I look forward to seeing you later on in the meeting. God.